Hi everyone, thank you for joining today. I want to talk a little bit more about those different layers of the sun with its zones and then also its atmosphere, and then really focus in on that core where that's going to create all of the energy that radiates all the way out through the different layers and zones of the sun. So let's just kind of review just a little bit from what we talked about a couple of days ago. So the sun is the closest star to us here on Earth. It is the most massive object in our solar system, holding everything together. It's an average size yellow dwarf star that is about midlife, and we're going to talk about what that means in relation to what is called the main sequence, which just says that it is fusing together hydrogen into helium, and that's what we're going to focus in on today. Remember that radiation is can be put into a particle format called photons. They are massless, but they have a frequency in which we can then figure out what is the energy moving through. And then we have our atmospheric layers of the sun, with the outermost layer, the corona, moving into the chromosphere where sunspots are formed, and then the photosphere, which is the layer that we see every day. If you were to just glance up at the sun, don't look completely at it. Today we're really going to focus in on these three layers: our convection zone, radiative zone, and the core. These are kind of that inner part of the sun, and also in other stars too. Don't think that this is just a one-time deal for our sun. This is all stars are doing the same thing, and we'll kind of wrap this all together a little bit more as we move forward and start talking about the life cycle of a star. But we have our convection zone, which is energy that is moving up and cooling off, sinking back down, warming up, rising, cooling off, sinking back down. You have that circular motion. And once again, this is plasma, our fourth state of matter. So it's electrically charged particles that are moving through, and they're electrically charged because of what's happening in the core. So we have our radiative zone, which is just radiating energy, our thermodynamics with radiation and convection, and then the core, that's where we're going to focus in today, is that it is the most dense part of the star, and it is fusing together hydrogen molecules. So it is just that it is so much pressure put underneath the core that it causes this fusion. And we talked a little bit about this, is that hydrogen burns and fuels together to form helium. So all stars start out with an abundance amount of hydrogen, and as they move through and start to fuse together, they are pretty much changing over their mass from hydrogen to helium. So it's an exchange. It's the law of conservation of mass. It's creating one and then changing it into another, fusing it together to create another. So, and that creates then what we call our main sequence star, which is hydrostatic equilibrium, meaning that it is productively producing a fusion from hydrogen into helium, and it's staying in a nice static state because gravity is pushing inwards and fusion is pushing outwards, and it's causing it to be balanced. So it's a static state, it's equal. Let's continue though and talk about some of the other features that you can kind of see that happen in the sun. The first is a wrap back to our magnetic field, which is, if you think about our magnets, these are electrically charged particles that once again have those protons, neutrons, and electrons are subatomic particles, and it says electrons that are being charged electrically that also create a magnetic field. So if we think about this picture here, this is a picture of the Earth's magnetic field, and we know that the convection in the core of our Earth, which is mostly made out of iron, is that it is turning that iron and creating these currents that radiate out from the North Pole and circle all the way around down to the South Pole, and it keeps doing that motion, keeps going through that. The sun, however, is significantly way much bigger than the Earth is. And so it does have magnetic fields as well, because you still have electrically charged particles there. It's just that it's not as nice and neat as what we see here on the Earth. the sun's magnetic fields actually are very strong and are generated due to sunspots in that convection zone. So we've got here the structure of the sun's corona is shaped by its magnetic field. Remember, the corona is that outermost wispy part, and the sun's magnetic field can vary on its strength. And that has wants to do again with how active the sun is going to be. And so the sun goes through what we call two different types of periods, solar maximum and solar minimum, which is about a 22 to 25 year cycle. Currently, the sun is in solar minimum, where it is not very active. We do not see a whole lot of sunspots, which therefore the magnetic fields are slightly weaker than what they would. And then it starts revving up its energy again, and then we start to get very active amounts of sunspots. These magnetic lines on the sun can actually be almost intertwined a little bit at times. So if we think about the Earth's magnetic field, it's all this nice little neat radiating from the North Pole down to the South Pole. But we can see energy moving through it when we get solar flares from the sun that then cause energy to bend our magnetic field. And so the sun has the same thing. It's just that there are times that some of those magnetic lines are going to get crossed because sometimes sunspots can become very close together. So magnetic fields can be thought of as lines that connect the north and south polarities. So it does come up like this, and here's an actual representation of it, and we'll look at some pictures here today in a little bit too. So magnetic fields connect opposite polarities just like they would north and south poles, just like our map would. So the sun's makeup. So let's kind of just talk about these inner zones of the sun. So once again, we have our convection zone and our radiation zone. So energy moves through the layers of a star by convection and radiation, are two different types of thermal dynamics. So think in that core, it's fusing together hydrogen and helium. So it is pretty much taking mass and creating energy. It's pushing together those particles of hydrogen to form helium. And as it does that, it's causing these huge explosions that cause energy to move outward. And that's where we have our radiation, is that idea that it is that movement of energy moving all the way through this radiative zone. So I'm going to start down here and then move up, just because think core, radiative zone, convection zone. So the radiation zone is just atoms are absorbing energy and transferring it to one another. So it's just heating up that whole zone area right outside the core. And then once it gets to the convection zone, it's starting to take that plasma and allowing it to rise up, and then it starts to hit that cooler photosphere and sinks back down. And when I say cool, I still mean it's really, really hot. It's just cooler than the convection and radiative zone. So we get that convection cycles moving in the sun. Brightness is also something really important I want to talk about just right now, with the idea that our sun is a yellow dwarf star, meaning it's actually kind of like mid-heat. And in space, it's kind of flipped on what you would normally think, is that red means cool, and our blue and our whites are actually really hot. So think back to our electromagnetic spectrum, where we had red and orange and yellow on one side with our long wavelength, low frequency. That's what we're seeing. So when we look at red and orange stars, that normally means that they're cooling off and they're losing their energy, and their mass is changed from several different elements. Whereas we see a very white, crisp, and sometimes almost bluish star, that means that its temperature is really, really hot. It's much more luminous. We'll use this term here in the next couple of days. Its luminosity is very, very bright. So stars will produce a full range of the electromagnetic spectrum. Our sun does that. It produces every wavelength. We get a lot of the lower wavelengths along with our UV. There are some X-ray and gamma that do blurp out of the sun just a little bit, but in low energy doses. And oh, I kind of jumped ahead here. Here's my idea of color. So objects glow with light that is short wavelength, closer to the blue spectrum, where cool objects glow with light that have a long wavelength, a red end of our spectrum. So let me see if I can, I don't know if I have a picture, I don't. There is a star that you can see pretty relevant almost every night. It is in the constellation Orion. So if you go out tonight, if it's a clear enough night, look for 3 stars that are really close together, almost in a line shape. That's Orion's belt. And if you look up to the star that is furthest to your left, so there's 3 stars, find the one that is farthest on your left and look up, you're going to be looking at Orion's shoulder. And in his shoulder is a star that is called Betelgeuse. Not like the movie, but it is named Betelgeuse. And if you stare at it just long enough, you should be able to kind of see that it is a almost reddish orange color. It's not as white as all the other stars. And that is a cooler star, meaning that Betelgeuse is actually on its way out. It's a red giant, and it's slowly, at some point, maybe in our lifetimes, will supernova, and we'll talk about what that all means as we move forward. But it is just that idea that it is cooling down just a little bit. So star temperatures can kind of change. So we normally see this orange and yellow and red, meaning that our sun is about midway through its life. It probably started out over here, and now we're kind of in this yellowish area. And as time marches on, in about 5 billion years, we'll see it move from orange and then into that red giant stage, which you and I won't be around for that, but maybe humans and civilization will still be here. So I am going to show you some pictures from SOHO when we get a chance, as we move into talking about our different ways of looking at images and the radiation that comes from the sun. I hope this was helpful. You can obviously visit this site and pull up different images of the sun as well, kind of just like filters to look at it through a radio wave, to look at it through an X-ray, and UV, and all the different waves. So hope this was helpful, and I'll see you guys soon.